In this video, KVA rating of an electrical generator is derived. As will be seen, KVA rating can be increased to a limited extent. Aim is to obtain maximum rating from the generator. KVA rating depends on various parameters. There is a limitation in increasing each parameter. Derivation of KVA rating of the generator is given. Volt ampere rating of three-phase electrical generator is equal to 3 VI. Terminal voltage V is approximately equal to induced EMF E. Thus, volt ampere rating may be taken as 3 EI. Induced EMF E is equal to 4.44 kW Fn phi. Speed n in RPS is equal to 2F by P. That is, frequency F is equal to Np by 2. E and F are substituted in the VI equation. Number of conductors per periphery C is equal to 3 into 2n divided by pi d. Hence, number of turns n is equal to C pi d by 6. Flux phi is equal to B pi d L by P. Number of turns n and flux phi are substituted in the VI equation. Current is in amperes. Distribution factor Kw is equal to Kd into Kp. Substituting, we get VA rating of the generator is equal to 11 Kp Kd d square ln BAC, or KVA rating of the generator is equal to 11 Kp Kd d square ln BAC into 10 to the power minus 3. Let us examine what is the limitation in increasing each parameter. Let us examine distribution factor Kd. Distributed winding reduces harmonics. It also ensures uniform temperature all around the stator core. It is approximately equal to 0.955. Hardly anything can be done to increase this parameter. Let us examine pitch factor. Even harmonics are absent in electrical machine. In star-connected stator winding, triplen harmonics are also absent. Higher harmonics are of lesser magnitude. Thus, fifth and seventh harmonics are of significance. Short pitch angle of 30 degrees is most suitable to reduce both fifth and seventh harmonic. Pitch factor with short pitch angle of 30 degrees is 0.96. Hardly anything can be done with respect to this parameter also. Large electric generators run at high speed, that is 3000 rpm, to increase KVA rating. These are of two-pole construction. Centrifugal force on rotor periphery is very large. Diameter is limited by the centrifugal force. Smaller electrical machines have stampings on the rotor. As the diameter of the rotor increases, both mass and radius of the rotor increases. Hence, centrifugal force, which is given by m omega square r, increases. Rotor stampings are not able to withstand large centrifugal force. Hence, in large turbogenerators, solid shaft called barrel is used. Since diameter can be increased to a limited extent, KVA rating of the electrical generator is increased by increasing length of the generator. If you have visited a thermal power station, you will see that turbogenerators have large length but less diameter. When the length of the generator increases, critical speed decreases. If critical speed coincides with the running speed, there will be resonance and hence high vibration and noise. Length by diameter ratio of the rotor is selected in such a way that critical speed is 20% away from the running speed. In a very large generator, critical speed less than running speed cannot be avoided. Rotor is called flexible rotor. Lot of expertise is required or dynamic balancing. This is due to the reason that mode shape in case of flexible rotor changes. In case of a rigid rotor, that is critical speed is more than the running speed, rotor vibrates as shown. Slow speed balancing is possible. In case of a flexible rotor, that is critical speed is less than the running speed, a node is formed and rotor vibrates as shown. One side of the rotor moves up while the other side moves down. Rotor is required to be balanced at running speed. Slow speed balancing is not possible. In case rotor is balanced at slow speed, balancing is disturbed at higher speed. Moreover, more balancing pins are required for balancing the rotor. Iron loss consists of hysteresis loss and eddy current loss. Both these losses increase with flux density. Moreover, there is a saturation in the flux density B. Let us multiply flux density with the area of flux path and H with length of the flux path. We get flux versus MMF curve. In a saturated region, more magnetizing current is required, resulting in lower power factor. Moreover, larger brush gear assembly is required to handle large magnetizing current. Iron loss is kept equal to copper loss to obtain maximum efficiency. In case flux density is high, iron loss becomes larger than copper loss and efficiency reduces. Higher ampere conductor increases temperature and may affect insulation. Insulation is very sensitive to temperature. For every 10-degree rise above permissible temperature, life of the insulation becomes half. Hot spot temperature may also be taken care of. Ampere conductors may be increased by increasing cross section of the conductor. However, larger stator slots are required. But cross section of flux path decreases. Flux density increases, leading to higher iron loss. Thus, there is a balancing act between copper loss and iron loss. Ampere conductors can be increased by better cooling. In very large turbogenerator, hydrogen is used as a medium of cooling. Heat carrying capacity of hydrogen is 8 times larger than that of air. Moreover, hydrogen is light and compressor is able to move more hydrogen in a cooling circuit. But hydrogen forms explosive mixture with air. Carbon dioxide is used as an intermediate medium to fill a generator. Carbon dioxide is an inert gas. Similarly, for taking out hydrogen from generator, carbon dioxide is used as an intermediate gas. In very large turbogenerators, stator winding is also cooled by passing water through hollow conductors in stator winding. Rating of largest generator in India is 800 megawatt and is installed in Jera. Some of the largest generators in the world are given.